Hi and welcome. I'm trying to learn particle physics, today quarks, and after we've done it, we're gonna do next stretching, and if you participate in the next stretching, then it's valid honors. Much remained unclear. For example, why certain combinations of quarks flourished and others didn't. So why of them turned more often up as other ones. You couldn't easily produce a composite particle made of 4 or 5 quarks, or even yet a quark on its own. Why was it? It was supposed to make... There were 2 pieces of evidence to suggest that quarks were more than just monsters in the mathematics. First, physicists firing electrons at protons noticed that some bounced off at right angles. This suggested that the electrons had hit something inside the proton, something like a quark. What's more, Gell-Mann's model indicated that certain combinations of quarks remained undiscovered, like the gaps in Dmitry Mendelev's original periodic table of elements. This gave the model predictive power. When the missing particles formed of combinations of all 6 quarks up, down, charm strings, bottom turned up as expected, the quark model's acceptance was nigh on guaranteed. Okay, inside of the protons themselves are some types of quarks. There are these up or down and 3 types of these 6 types of quarks. And now we're wondering, you couldn't easily produce a composite particle made of 4 or 5 quarks. There are always 3 in them, obviously. Or it seems that. Whatever get a quark on its own. Why was it? So there were always 3 inside of one proton. The answer lies in the property of color charge, which bears no relation to the colors we think of in daily life. Color is something we just pick to name it because it comes in free. Says Freya Blackman at the Free University of Brussels in Belgium. Quarks of these different colors, called red, green and blue, can sit together because the color charges cancel out, by analogy with the way different colors of light blend together to make white. So, all with it. No, why wasn't it exactly? Color is something we've just picked to name it because it comes in threes. So it has nothing else to do when it was in 3. Not that these 3 have something similar like blending out as it is with red, green and blue, do we see? To make white. Red, green and blue. Are these the 3 things used in LEDs? And is when white on an LED on a screen made with making all 3 on? Whatever. It seems to be just about 3. Let's use it again. I want to know, is it just about 3 or is there something else similar? No relation to the colors we think of in daily life, so nothing to do with red, yellow, green, whatever. Color is something we just picked to name it because it comes in 3. Says Freya Blackman at the Free University of Brussels in Belgium. Quarks of these different colors, called red, green, blue, can sit together because their color charges cancel out. Because they're color charges. Because in one proton there are up or down, up and down, or charm, strange, whatever, but not in every combination. Is the way to say here. This is why there are not 4 or 5 or not 1 alone. It has something to do with it. We're gonna read on my figures update. Maybe this is something to do with the jar is actually 3, and so it's more than just that we're 3. It's also that these 3 are always 3. They cannot be 4 or 5 or 1, because together these 3 will fit together as the 3 colors red, green and blue. Also, if these 3 colors come together and make white, do we say, whatever. Through the same logic, a quark and an antiquark could sit together, assuming they had color charges of red and anti-red. Okay, inside of this proton, or neutron obviously also, there can be one anti and one other one. Where was it? Can an anti one and another one if they have a quark and an antiquark, if one of them has red and the other one anti-red as type. This also explains why single quarks don't fall out of atoms in detectors. Without their color partners, they are too unstable. And what happens with them if they have? Okay, and there are always when these 2 one anti and the other one. Quarks are always team players, says Freya Blackman. By the end of the 70s, we finally had what is still the most complete description of quarks and the strong nuclear force that binds them together. Quantum chromodynamics. QCD. Quantum chromodynamics. Named Name for the color charge that quarks possess. The trouble is, QCD turns out to be horrendously complex theory to deal with. By the end of the 70s, we finally had what is still the most complete description of quarks and the strong nuclear force that binds them together. So the strong nuclear force is binding together the quarks. Quantum chromodynamics is it named for the color charge that quarks possess. And the difficulty is, the trouble is, quantum chromodynamics turns out to be horrendously complex theory to deal with. Take a simple question as to the difference between protons and neutrons. For example, obviously protons have a positive electrical charge, whereas neutrons have a neutral. But we also have ever so slightly variant masses. In the units that particle physics use, the neutron weighs in 939.6 mega electron volts and the proton at 938.3, so 2 megavolts difference. Both around 1,800 times meteor. Do we mean mightier? Meteor? Mightier than the electron. Okay, the first thing is, proton and neutron are 2,000 times more massive or weightier than an electron. Electrons are the thing, as far as I understand, which are transporting electricity from one place to another. Would it be more difficult to build wires if it would be transported from protons, which are 2,000 times more heavy? Are they slower, the protons? It would make a bit sense because they are in the nucleus and the ones on the shells. It would be all the storage. Okay, 939. So the neutron and the proton have a little bit different mass. The proton is positive and neutron neutral. The difference between their masses is just 0.14%. But boy, does it matter. Okay, they have just a tenth of a percent in difference in the mass. The neutron's extra mass means, yes, the neutron is heavier. No, the neutron is less heavy. Neutron weighs, the neutron is heavier. Neutron is heavier, 0.1%. The neutron's extra mass means neutrons decay into protons via beta decay, not the other way around. Neutrons are decaying into protons. Maybe we said something wrong, so did we set it in some place? Maybe if a beta plus decay is happening for protons into neutrons, they are not decaying into neutrons, because they cannot. The neutron's extra mass means neutrons decay into protons via beta decay, not the other way around. So I'm saying the neutron weighs 0.1% more than a proton, and therefore it can decay into, when it does beta decay, into a proton. But the proton cannot decay into neutron because it has 0.1 less mass, and it would need it to become neutral, does it have to get an electron, and something which does not have it cannot decay into it. If a neutron has inside of it all the things necessary to build a proton, and also the things, and it is neutral because it has the things of a proton, but also some electron in it. It is neutral because it has proton and electron in it, and now if it decays, it can become a proton by giving off the electron. But the proton cannot become a neutron because it does not have electrons in it. For a proton to become neutral, it has to somewhere buy its electron. Let's go for a more break. In radioactive beta decay, in the most common form of this decay, beta minus decay, a neutron decays into a proton and spits out a negatively charged electron to conserve the electric charge. Beta plus decay does the reverse and turns proton into neutron. Okay, somehow is a somehow still possible, but there seems to be a difference every other time. When neutron's extra mass means neutrons decay into protons via beta decay, not the other way around. Our current best guess is that the proton's half-life, a measure of its stability over time, is at least 10 to the 32 years, so this is very, very, very long. Yes, just want to say, given that the universe only has a 10 to the 10th or so years behind it, that is a convoluted way of saying no one has ever seen a proton decay. Protons take billions of times longer to decay as the universe is old. En kan je dan hebben we via plastic proton? The persistence of protons means they can team up with negatively charged electrons to form robust, structured, electrically neutral atoms, rather than the world being a featureless. What? Rather than the world being a featureless neutron glob. The persistence of protons means they can team up with negatively charged electrons to form robust, structured, electrically neutral atoms, rather than the world being a featureless neutron, whatever. Okay, protons can become neutrons, but they have to team up with an electron to become neutron. The neutron itself can just split off, become a proton, and splitting off the electron. Now, this was the electric, now it was the particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics. We will do the next stretching. If you stay and participate in the next stretching, that's really honest. We're starting with a hydro tower. Have a good step state. And we're breathing in the arms up. And reach as far as you can with the fingertips. And if you participate, that's really honest. Then reach as far as you can with the fingertips. High up, breathe in, and down, and reach. Continue to reach as far as you can with the fingertips. And another one. Reach as far as you can. Down again, reach still with the fingertips as far as you can. And now another exercise. Reach as far as you can with the fingertips. Go in front. Go up. Not just to the sides, but also back. Reach as far as you can. And another one. Reach as far as you can. And back and reach as far as you can. And now, a buzzard, I think. What's the buzzard in the one? The buzzard. You have the feet same together, arms up to a T, and pretend to fly around like a buzzard. And now the police officer. Feet are standing as a do. Everything in the arms up. Without on the side. In and out. Out to the other side. In and out. And out and down. Now I have feet standing shoulders wide apart, tall up, breathe in, shoulders back, and breathe out, bring the head over to one side. Breathe in, and out, chin down to the cloak. Breathe in, out, lift the gaze and turn it back. To the middle, over to the other side, tall up, shoulders back, breathe in, out, chin down to the cloak. Breathe in, lift the gaze, bring the head over to the other side. Breathe again in, and breathe halfway out, and then circle over to the other side. Again in, and out, circle over. Now we fly. Bring the palms together, and the elbows together, breathe in, and lift up. And out and down. And again in and up. And out and down. Next exercise, hands together, breathe in. And out, reach in front and bring the head down. In the back. Out in front. And now the cash, you have the feet standing together, intertwine the fingers behind the back, tall up, shoulders back, breathe in. And out, chin over, head over to one side, chin down to the clavicle, breathe in. And out, reach with the hands down to the ground. Breathe in, lift the gaze, turn the head over to the other side, tall up, shoulders back, breathe in. Out, chin down to the clavicle, and pull with the hands down to the ground. Breathe in, lift the gaze, and back into the neck. And now I have the feet standing, shoulder wide apart. Now still together. One arm behind the back, breathe in, lift one arm up, tall up. And out, bring the head over to one side. Just bring it over, don't pull. Down again, the other hand behind the back, other hand up, and bring the head over, down, just bring it over, don't pull. And back. And now breathe in and lift the arms up. Breathe out, lean back, draw the shoulder blades together for the grip in the body. In and up. And out again, down. In and up. Out and down. We're doing a few eagle swings. Breathe in, lift the arms up. Out and down. And in and up. Bring the heads to touch, allow the hands down to heart center. That was the next stretching. Thank you very much. Until next time.